Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video on limits is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we'll be discussing the definition of a limit, solving limits by substitution, solving limits by factoring and using conjugates, one-sided limits, infinite limits, and limits at infinity. Suppose a function f is defined for all x near a except possibly for a. If f of x is arbitrarily close to L for all x sufficiently close to a, we write the limit using the following notation, and we say the limit of f of x as x approaches a equals L. We can also say that the limit of f of x as x approaches a equals L if f of x gets closer to L as x gets closer to a. The values of the limit depends on the values of f near a, but does not depend on the value of f of a. The idea of a limit can often be understood better by seeing it on a graph. Let f of x be described by the graph to the right. If we were to evaluate the limit as x approaches 1 of f of x, we look at the graph and observe how the graph behaves as x gets closer to value of 1 from both sides. In this case, we see that f of 1 equals 1, and as x approaches 1, f of x also approaches 1. Therefore, the limit is equal to 1. In the second limit, we look at what happens as the limit approaches x equals 2. In this case, f of 2 equals 3, but we see in the graph that as x approaches 2, f of x approaches 2. So the limit for f of x as x approaches 2 is 2. In the third limit, we look as x approaches 3. Here we see that f of 3 is undefined, but as we saw in the previous limit, we are looking for the behavior of the function as it approaches the limit. In this case, the limit of f of x as x approaches 3 is equal to 3. For many functions, the simplest solution involves directly substituting the limit into the function. The limit of f of x as x approaches a equals f of a. This method is sufficient for all linear functions and polynomial functions. For example, let's evaluate the limit of 2x squared plus 3x minus 2 as x approaches 1. In this case, we simply substitute 1 for x and complete the arithmetic. In this case, the limit equals 3. There are, however, limits that cannot be solved by direct substitution. In these cases, the limit may exist, but simple substitution leads to an inconsistent or undefined solution. The limit of f of x as x approaches a is not equal to f of a. For example, let's look at the limit of x squared minus x minus 6 over x minus 3 as x approaches 3. If we use substitution, we arrive at 0 over 0, which is called indeterminate. Upon closer examination, however, we notice that the numerator in our example may be factorable. Once the factor is taken and cancelled with the term in the denominator, we can use substitution to arrive at the limit, which is 5. A similar technique using a conjugate may also be used in solving a limit that appears to have no solution when using substitution. For example, let's evaluate the limit of the square root of x minus 2 over x minus 4 as x approaches 4. If we use substitution, we arrive at 0 over 0, which is indeterminate. Find the conjugate of the term containing the root and multiply that value to both numerator and denominator. In this case, the conjugate is the square root of x plus 2. When we multiply this in the numerator and denominator, we get a term that cancels with the original denominator. The simplified form of the function can now be solved with substitution. In this case, the limit equals 1/4. Assume that the limit of f of x as x approaches a and the limit of g of x as x approaches a exists. The following properties hold where c is a real number and n is greater than 0 is an integer. The limit of the sum of the two functions equals the sum of the same two functions' limits. The limit of the difference of two functions equals the difference of the limits of the same two functions. The limit of a constant times a function is equal to that constant times the limit of the function. The limit of the product of two functions is equal to the product of the two limits of the same function. The limit of the quotient of two functions is equal to the quotient of the limits of the same function, assuming the function in the denominator is not equal to 0. The limit of a function taken to a power is equal to the limit of the same function taken to the same power. The limit of the function taken to a root is equal to the limit of the same function taken to the same root. This holds if f of x is greater than 0 for x near a if n is even. A limit is evaluating how a function behaves as it approaches a given independent variable. Some functions behave differently depending on which direction the variable is approached. For a right-sided limit, suppose f is defined for all x near a with x greater than a. If f of x is arbitrarily close to L for all x sufficiently close to a with x greater than a, we write the limit of f of x as x approaches a from the right equals L. For a left-sided limit, suppose f is defined for all x near a with x less than a. If f of x is arbitrarily close to L for all x sufficiently close to a with x less than a, we write the limit of f of x as x approaches a from the left equals L. Let's consider the piecewise function described by the graph to the right. Notice how the function is not continuous across x equals 2. But if we confine our limit to be from the right, then the limit of f of x as x approaches 2 from the right is 6. Conversely, the limit of f of x as x approaches 2 from the left is 3. Since the left and right limits are different, the limit of f of x as x approaches 2 does not exist. Suppose f is defined for all x near a. If f grows arbitrarily large for all x sufficiently close to but not equal to a, we write the limit of f of x as x approaches a equals infinity. A similar limit can be written if f of x is negative and grows arbitrarily large. The limit of f of x as x approaches a equals negative infinity. In these cases, the line x equals a is a vertical asymptote. As an example, let's evaluate the limit of 1 over x as x approaches 0 from the right. If we observe the graph of 1 over x, we can see that the graph does not intersect the y-axis. By charting given values as x gets closer to 0, we see that f of x gets much larger, so the limit is infinity. Likewise, if we do the same with the limit as x approaches 0 from the left of 1 over x, the same thing is happening, but on the negative side. Charting our values, we see that as x approaches 0 from the left, the limit approaches negative infinity. In these cases, 0 is a vertical asymptote. If f of x becomes arbitrarily close to a finite number L for all sufficiently large and positive x, then we write the limit of f of x as x approaches infinity equals L. In this case, the line y equals L will become a horizontal asymptote. Likewise, if f of x becomes arbitrarily close to a finite number m for all sufficiently large and negative x, then we write the limit of f of x as x approaches negative infinity equals m. In this case, the line y equals m will also become a horizontal asymptote. We can use the same function to describe a limit at infinity. This time we'll evaluate the limit of 1 over x as x approaches infinity. Again, referencing to the graph, we see that as x gets larger, the value of f of x approaches the x-axis. Putting our values in a chart, we see that the larger x gets, the closer f of x gets to 0 without reaching it. The same is true if we evaluate the same function as x approaches negative infinity. Looking at the graph and the chart, we see that the larger the negative values get, the closer f of x gets to 0 without reaching it. In these cases above, 0 is considered the horizontal asymptote. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.